In this lecture, we will learn about heats of formation and how to calculate delta H of a reaction. Certain types of chemical reactions have special names for their enthalpy change. For example, the enthalpy change of a combustion reaction is called heat of combustion. In this example, the heat of combustion of 1 mole of methane gas is negative 890 kilojoules, which means 890 kilojoules of heat is released when 1 mole of methane is completely burnt. The reaction shown in this example is a formation reaction, and the delta H associated with this reaction is called heat of formation, and it is represented by delta H sub F. It's also called enthalpy of formation. Enthalpy of formation is the enthalpy change for the formation of a compound from its elements. If you examine this reaction has a compound on the right-hand side, and its constituent elements, nitrogen and hydrogen, on the left-hand side. It's a reaction in which ammonia gas is formed from its elements, nitrogen and hydrogen. Now let's understand what standard enthalpy of formation is. Standard enthalpy of formation is represented by delta H sub F naught. The circle on the top represents a standard condition, which is 25 degrees Celsius and 1 atmosphere pressure. Standard enthalpy of formation is the enthalpy change for formation of 1 mole of compound from its elements in their standard states. The following reaction represents a reaction for standard enthalpy of formation of ammonia gas, because 1 mole of ammonia is formed from its elements. The elements in this reaction need to be balanced. In the balanced equation for this reaction, you would have a coefficient of half for nitrogen and a coefficient of 3/2 for hydrogen. Notice that on the right hand side, the coefficient must remain 1. So it's okay to have fractional coefficients on the left hand side. For this reaction to represent a standard heat of formation, the elements also need to be in their standard state. Let's consider what a standard state is. The standard state of an element is its stable elemental form at 25 degrees Celsius and 1 atmosphere pressure. This temperature is approximately room temperature, and the pressure is approximately atmospheric pressure. It's the atmospheric pressure at the sea level. This condition is referred to as a standard condition. Let's consider the standard state of some elements. The standard state of hydrogen is diatomic hydrogen gas, because hydrogen occurs as a diatomic molecule and it is in gaseous state under standard conditions, which are approximately room temperature and atmospheric pressure. Similarly, oxygen, nitrogen, fluorine, and chlorine are diatomic molecules, and they occur as gases at 25 degrees Celsius and 1 atmosphere pressure. All noble gases occur as monoatomic molecules. Notice that helium is by itself and doesn't have a subscript like 2 in the case of diatomic molecules. Noble gases exist as gases under standard conditions. Among the halogens, fluorine and chlorine are gases. Chlorine is a light greenish colored gas. Bromine is a liquid at room temperature. Standard condition 25 degrees Celsius and 1 atmosphere pressure. Remember that it is close to room temperature. Bromine occurs as a liquid under these conditions. Iodine is a solid under standard conditions. So these would be the standard states for bromine and iodine. Mercury is the only metal which exists in a liquid form at 25 degrees Celsius and 1 atmospheric pressure. You may be familiar that mercury is a liquid at room temperature. All other metals are solids. So potassium would have this state as the standard state, and this would be the standard state of copper. Another important standard state you should be aware of is carbon. Carbon's standard state is a solid in the graphite form. Now let's write the standard enthalpy of formation of solid sucrose, whose formula is C12H22O11. Standard means 1 mole of sucrose should be formed. So 1 mole of C12H22O11 should be on the right hand side of the chemical equation. The elements involved are carbon, hydrogen, and oxygen, and you would need to form the compound from carbon, hydrogen, and oxygen in their standard states. Next, balance the chemical equation. Some coefficients may end up as fractions since you have to maintain a coefficient of 1 on the right hand side. Standard enthalpies of formation are well-known values that can often be looked up. In this table, the standard enthalpies of formations for various substances are listed. Standard enthalpy of formation of sucrose solid is negative 2221 kilojoules per mole. Therefore, the standard enthalpy of formation, which is the enthalpy of formation for this reaction, would be negative 2221 kilojoules per mole, which means 2221 kilojoules of energy is released when 1 mole of solid sucrose forms from its elements. Also notice that the standard enthalpies of formations depend on the states of the substance. If you're talking about standard enthalpy of formation of liquid, it's a different number from the standard enthalpy of formation of water in gaseous state. What is the enthalpy of formation of O2 gas? Notice that O2 gas is already a standard state, so it's not forming from anything. So enthalpy of formation of O2 gas would be 0. Heats of formation of elements that are already in their standard state is 0. Therefore, standard heat of formation of fluorine gas, bromine liquid, potassium solid, carbon solid in its graphite state would all be 0 because these elements are already in their standard states. Now, how to calculate the delta H of a reaction that is not a formation reaction? The formula to calculate delta H is take the total enthalpy of formation of all your products and then subtract the total enthalpy of formation of all your reactants. That's the formula. Let's take a look at an example. So here's your reaction, and our goal is to calculate the delta H for this reaction. So you can look up the standard enthalpies of formation of each of your product and reactant molecules in a table that may be provided for you. So you need to be provided with enthalpies of formation values in order to find the delta H of this reaction. So let's start with the products. Carbon dioxide gas. So carbon dioxide gas has a delta HF value of negative 393.5, but this is per mole. And since we have 3 moles of carbon dioxide, you have to multiply that number by 3. You can do the same thing for water in liquid form. Notice that you have 2 enthalpies of formation values for water, one for liquid and one for gas, and make sure you pick the right one. Having the right state is important. Remember, enthalpy depends on state. So since negative 285.8 is enthalpy of formation for 1 mole, you have to multiply it by 4 moles for 4 moles of water. So you do the same thing for C3H8 gas using its enthalpy of formation value. You have only 1 mole. What about O2 gas? What is its enthalpy of formation? It's going to be 0 because O2 gas is already in standard state. Now you use the formula. Delta H would be total heat of formation of all your products. So add up those 2 numbers. And then you subtract the sum of these 2 numbers. And you would end up with negative 2,220 kilojoules, which is heat released. And this is a combustion reaction, so you would expect a lot of heat to be produced in this reaction. So that's the way to calculate delta H of any reaction if you know the standard enthalpies of formation of each of the reactant and product species that are involved.